Okay, so I'm going to just talk about Psy ShareD, really, introduction, and I sort of appreciate that some of you will have heard this before, but I think it's sort of worth going over, and there are also updates as well. I have to acknowledge UKRI Medical Research Council, who provided the initial funding, and the NIHR Biomedical Research Council at King's or Maudsley, who are giving us funding now going forward. So just those acknowledgements. The team initially is here. So myself, Matthew Kempton, Vina Kamari, Jack Rogers, Rachel Up the Grove, Simon Evans, Mariana Zurita, Ruba, who's here today to talk, and Sarah, who's left the project, helped us in the initial phases of setup. So a big thank you to everyone who was involved in the initial grant application, and also to acknowledge all the other co-Is who are kind of here somewhere. So people like Graham Murray at Cambridge, and the people at Edinburgh, and Oxford, and so on. As you can see, we've sort of expanded quite significantly in the first couple of years. So I think broadly the way this is arranged is that the sort of applicants on the original funding are at the top, but you can see now we have several international partners, and most recently we've been joined by universities in Berlin, in Taipei, Georgia State University, and I think we have our first Chinese partner now as well. I'll talk a little bit more about the sort of geographical sort of spread in a few slides' time. Here are some publications that have been published. So if you want to know more, there's 3 publications that you can currently access that describe Psy ShareD, sort of how it works. I think the best paper for that is the HBM paper, but also Simon and I published a few papers, or Simon's led on a few papers that provide more of a narrative as to why we think Psy ShareD was needed in the first place, and what sort of gaps it sort of fills. Our validation of harmonization procedures paper is currently in submission with HBM. Those of you that were maybe at the Chicago meeting, the SIRS Chicago meeting, would have seen that presentation by Mariana back in the spring, and we're hoping to get that published early next year. Okay. So I'm just rearranging my screen a little bit. Why is Psy ShareD needed? So the primary objective of Psy ShareD is to build a free-to-access MRI T1 data repository from pre-existing data sets across schizophrenia and psychosis risk populations. Importantly, for that to be useful, we need to have the linked clinical, demographic, and cognitive data. And we need to try and acquire these data sets in diverse populations. So the resource currently includes T1 data in people with schizophrenia, with first episode psychosis, clinical high risk for psychosis. We also have some sort of risk factor phenotypes, so in personality and environmental risk. We're trying to build the longitudinal data resource as well. So we currently have longitudinal data that I'll give the numbers shortly, but we're looking to expand on that. And of course, we also have a big resource of demographically matched healthy controlled populations. And I think in the future as well, we're kind of keen to maybe expand beyond the psychosis phenotypes as well. I mean, we already have some data in small data sets in bipolar, in major depression disorder, and certainly we'd like to sort of build those going forward. It's just a question of sort of resources and capacity for being able to do that. So what do we do? So what we've been doing for the last sort of 2.5 years in terms of building the database is it all starts off with sort of contacting potential data contributors, of whom there are many now. The data needs to be subject to data sharing agreements that is coming from external institutions into King's College London. The contributors then retrieve the data once the DSA is set up, and I've heard some quite funny stories about people trying to locate and retrieve data sets from from years ago, finding where their hard drives at the bottom of boxes in cupboards and things like that. but I think we've got there with all or most of the data. The contributors then need to do some data preparation steps before the data can be transferred to King's College London. These are mainly sort of defacing and anonymization procedures. And then the data can be uploaded to a GDPR compliant platform for transfer, which we'll talk a little bit about. We've got a slide on that. I don't know, Ruba, you may want to say a little bit about that when I get to that slide. The data is then transferred to the KCL neuroimaging networks servers. We then process the data and make it available through data catalogs, etc. Has everyone got their Teams muted? Because I'm getting a little bit of sort of feedback on my voice. That's better. Thank you. Okay, so that's broadly what we do. So in terms of the latest updates on sort of members and site, we have pretty good geographical coverage. Still sort of working on South America, although we do have data sets in Mexico, so Central America is represented. As you kind of maybe would expect, most of the data sets are in Europe. I think there are 5 centers, or most of the sites are in Europe. Sorry, there are 5 centers in the UK and several others across Germany, Italy, Switzerland, Netherlands. And we also have fairly good coverage in Asia as well, in India, Singapore, China. We also have some sites in Spain, actually, which have come online recently as well. And we have sites in Japan. So it's been quite successful in that regard, in kind of trying to achieve this global coverage. I think we've done quite well. There are a few spots, obviously, that we need to work on. And we're hoping they will be, certainly Australia, Melbourne is hopefully in the final phases of a data sharing agreement that's been sort of going on for a little while. There have been some changes at Melbourne, so their sort of administrative side has been changed around a little bit. We've also signed off a data sharing agreement with Copenhagen, the Copenhagen group. So we haven't had the data transferred yet, but we're hopeful that will come across in the next month or two, and that's a rather large data set. Also at Mount Sinai in New York, Tokyo, and Kyoto. So, we are sort of continuing to expand the data resource and achieve sort of greater global coverage as well. And the idea is to sort of continue this. Again, we may have some limitations, constraints around capacity, but I think we should be able to sort of continue at some rate of expansion over the next year or so. So what about the data itself? So Ruben and I went through this on Monday, just to sort of get the most up-to-date numbers. So currently there are 21 partners, so they're partner institutions, and they're providing 51 data sets of MRI T1. Those are mostly raw T1 scans. There are some centers that are providing free surface style data only, 2 or 3 of those, I think. But the number of participants we have in the resource currently is 4,809, which, by the way, our initial target when we put the funding application in back in 2022 was 2,000. So, we've gone way beyond that, and hopefully that will continue to grow. In terms of the breakdown across phenotypes, the schizophrenia, as you kind of expect, is the largest phenotypic sort of group. But we also have really good numbers with first EP and clinical high risk. You can see they're both over 500. Schizotypy, so that's generally assessed with the SPQ. There may be some variation in terms of the measures used there. Bipolar, we now have 144. Again, very much looking to sort of expand those numbers along with depression and other diagnoses. Healthy controls, we have 1,615, and just under 100 of those have a very comprehensive childhood trauma assessment. Actually, this is what we need to do going into some of the 1,650 healthy control groups, certainly for the clinical high risk studies that we conducted at King's back in, around 10 years ago or more now. a lot of the healthy controls in those data sets would have received CTQ measures or similar sort of childhood trauma measures. So we can sort of go in, look at those and try and quantify that. So that number with CT assessments will be larger. Currently with case follow-up, we have 281. Again, that's an area we look to expand upon. And there's healthy control follow-up in 67 HC cases or participants. So those are the numbers. Is that icon to the right slide there? Yep. So I don't know, Simon, are you in the room? This is something that you've written about quite a lot.
I am.
In those papers. So I don't know if you want to sort of come in here on why Psy ShareD is needed, but I've kind of broken it down into sort of 4 points really. So some, not all multi-site and data sharing initiatives restrict access to consortium members only. And of course that kind of leads to inequity, particularly for early career researchers. So Simon, I know we've had some criticism for saying that, but I think, you know, that is kind of our experience. Do you want to sort of speak to that very quickly?
Yeah, I think we can stand by that, because the conversations I've had with some partners who are also part of other consortia agree that it is very difficult, if not impossible, for non-consortium members to access data from things like Enigma. So I think we can legitimately make that claim, definitely. I mean, the point of, you know, ultimately we recognize there's lots of legacy data out there, and ultimately, you know, a lot of resources and time have gone into collecting all of these scanning studies over the years that mostly is just sitting in a hard disk somewhere. Yeah. So that's the real motivation here, is to gather together all of this wonderful data that's being collected and allow researchers, regardless of where they're based and what resources they've got, to be able to do well-powered analyses on it.
Yeah, I think that's that, you know, the sort of democratization really was the primary objective, I think. You know, and other objectives really were to try and acquire data sets from, you know, geographically diverse locations, and you've seen that we've achieved that to some degree, although there are still areas that where we need to do more work. You know, and this is important. So there's been a lot of research that suggests that sort of ethnocultural factors do have you know, an effect on sort of schizophrenia in terms of prognosis, certainly. However, many brain-based investigations into schizophrenia have been conducted in the global north. That has changed quite a lot over the last sort of decade or so. Certainly with China, so much research now being published from China, and more being coming from South America and Central America. But I think if we can facilitate that by including data sets from all geographical locations, then I think that could help, you know, get at some of these questions about sort of ethnocultural effects in terms of schizophrenia pathology, diagnosis and prognosis. So that's really important to us. I suppose, Simon, again, going kind of back to the Enigma approach, and we aren't being critical of Enigma or trying to compete with Enigma. In fact, quite the opposite. You know, we're working alongside Enigma, and I think Matthew will talk a little bit about that in his presentation in a minute. But again, with Enigma, as many of you will know, it's kind of restricted to these, how would we describe them, sort of meta-analytical approaches. Simon, do you want to speak quickly about that?
Yeah, so I mean, in recent years, we're starting to see more of these mega-analyses where consortia like Enigma agree on a hypothesis and research question, and then go back to their data, and either each individual site conducts a standardized processing pipeline on it, or the data is transferred to one site. So one group does reanalyzes it. But those mega analyses are still relatively few and far between, and of course, far better than the traditional meta-analysis approach. So we are facilitating mega-analyses, and that's our primary aim here, because we gather together the data centrally, we collect the raw T1s, and then we harmonize it and run the FreeSurfer pipeline on it. So that means that for the user, unless they want to do VBM, for example, that they don't have to. They can just access the process FreeSurfer outputs and, you know, be reassured that it's all been harmonized and standardized. So we are very much prioritizing the sort of mega-analysis way of doing things. And in almost all cases, we have got that raw T1 data. There's a few data sets where only FreeSurfer outputs are able to have been provided, but in most cases, we have worked with the raw data, quality checked it, and run a standardized pipeline on it.
Yeah. Okay, thanks, Simon. And yeah, just the sort of final point there is, you know, other consortia have been sort of fairly restricted to single phenotypes, which then obviously makes it difficult to make any do any research across sort of trajectories. So by having a kind of continuum of psychosis phenotypes, if you like, if that's a good phrase, you know, you could do that sort of work with Psy ShareD. Like many of the Enigma consortia sort of focus in. So I'm a member of the schizotypy one and the clinical high risk one, but it's very much focused in on single phenotype. So, you know, again, that's something we're looking to sort of break out of a little bit, or with Psy ShareD. Okay, so how to use Psy ShareD. I'm guessing there'll be a few people in the room who maybe are thinking about putting in an application to access Psy ShareD data. So the first port of call for that is the website. I was going to do one of those things where I kind of did the website live, but sometimes when I try that, it doesn't work. So I've just done some screenshots just for the sake of simplicity, but the homepage is there. I think if you just type psyshared.com into your search bar, it should be sufficient, I think. And you'll land on the homepage, which looks like that. So we have the latest news. So yeah, Graham, we could put this video up there actually, if we can do that. So that would go somewhere like in the news section. We also have information on new projects that have been approved. I think there are currently 6 or 7 that have been approved. I mean, bear in mind that we have to update the website sort of, you know, that's obviously a very sort of proactive process that we do maybe once every 2 months or so. So it's not always completely up to date, but we do try and stay on top of it. But I think there are at least 6 or 7 projects on there at the moment. So it tells you a little bit about the projects and who the leaders of those projects are. And you know, I think that's quite an important resource for everyone really, if they wanted to get involved in projects, particularly also. I mean, all data sets will have been approved by the PIs of each data set anyway, so they should, well, they are aware of the projects that are happening. But I know people are busy and they don't necessarily look at everything that comes through on an email. But if they wanted to go and see where their data is being used, or remind themselves where their data is being used, then they can look on the project tab there on the website. In terms of people wishing to use the data, so the data, we have data catalogs which are accessed via the website. So that would be the page there at the bottom. This is just a screenshot, so it's not sort of interactive, but it's I think this is the top and the bottom of the data set table. So data sets are listed here. So about a quarter of all the data sets, maybe a third, are KCL data sets. So these are listed here with the corresponding data set ID. There's some brief information about the the diagnosis types that are included in the cases that are included in each data set, whether there's follow-up or not, and so on. Here we go. This is the sort of bottom of that page here. So Ruben, these ones still have to link, do they, to the Chord system at King's? That's why they're not live, they're not active links yet. Is that correct?
Yeah, if you go to that website and click on those particular link of those data set, you will see more details of the data, Like
Yes.
we are actually put the summarization of the data here. But if you go to those links, it will give you more details about the data set. And the last four, actually, the service is not working right now. That's why there is no link, but we will sort it out soon.
Shortly, yeah.
Yeah.
They said that would be up and running again in the autumn, didn't they? So we need to get on to them to make sure that. But yeah, so you can click on these on the data set. So if you wanted to look at Zurich 01, you'd click on there, and it would take you to a King's College London Figshare server or system, and that would give you much more detailed information about the data set, including papers that have been published from it, information about the PIs, more information about the clinical and cognitive variables. So that would be how you select your data sets if you were thinking of putting in a data access application. There are also tabs at the top here that are important to read as well about the data access procedure. Am I going the wrong way now? About the data access procedure and guidance, and I think we'll get to that in a minute. In terms of the linked data, yeah, it tends to break down sort of three clusters: clinical linked data, so caseness, assessments, generally PANS, CALMS for clinical high risk, and so on. SPQ, Hamilton A and D. I mean, as you can imagine, with putting together retrospectively collected data sets, there's a lot of variation. I think most have PANS, if not all. There might be a few really old ones that have SAPs and SANS, but most will have PANS. And as I say, all the clinical high risk, I think, I don't know about, I don't know if there's clinical high risk that's come from Lübeck that uses a different measure of clinical at-risk assessment, but yeah, most will have the CALMS. There's also information about medical status. This can be quite variable. Some of this is very simple, medicated, yes or no. Some of it's far more sophisticated in terms of, chlorpromazine equivalents and that sort of thing. Medication follow-up information. So if you wanted to do a treatment resistance study, you might want to look at what medication information is available within each data set. Demographic information is there, I think, in all data sets to a large degree. Maybe education is a bit more patchy, things like that, but certainly age, sex, and ethnicity will be there, I think, for all of them. Cognitive and IQ. IQ tends to be a sort of pre-estimated sort of IQ like NART or RAT or something like that. And there's working memory, verbal fluency data in a lot of data sets. Again, as you can imagine, tests used very considerably. So yeah, you'd have to sort of look at that carefully if you wanted to do a study or select data sets to do a study around cognition. So data preparation and transfer. So I'm just going to try and go through these last few slides quite quickly. So I think we've talked about this sort of data transfer sort of procedure protocol already. Once a data sharing agreement is completed, the contributing site will complete a data sharing template which sort of characterizes and documents all the data that's being sent to us. So that's reasonably standardized for us to process. They then apply defacing and anonymization scripts to the data, which is then uploaded to Bitbox. That's then stored on the KCL neuroimaging servers. Then we undertake some data processing. So the data will be available in sort of group T maps, but also in FreeSurf outputs and in sort of raw T1. We've done some harmonization work. Mariana isn't here today. She's no longer working on the project, unfortunately, but Mariana has done some great work along with Ruba on the harmonization steps. Briefly, we have image level harmonization using Hacker3 and CycleGAN, and we have feature level harmonized data using Combat. And actually, I think what we're finding with a lot of the data access requests now is that people are just sort of happy to take the data as it comes and sort of undertake their own sort of harmonization procedures with some support from us where necessary. But yeah, the harmonized sort of formats are available. Ruba, do you want to say something very quickly about Bitbox? This is just how the data is transferred to King's College London.
Yeah. Yep. So here some of them are actually already used it. It's just a transfer system to transfer the data from remote site to King's server. So it's a temporary transfer system only. We are not storing any data here. Once we have the data in the Kings and we are happy with the data quality and everything, we just remove it from the Bitbox. And yeah, that's because it's always difficult to transfer the data. Like we have that security issues and also access control, with the King servers. So it's the Bitbox. It's a website that can actually easily use from any all over the world. And yeah, it helped a lot to get the data in for our project in this King server. Yeah.
Okay, thank you, Ruba. So the harmonized, yeah, I've kind of covered this, I think, actually, in the previous slide. But yeah, just to sort of reiterate that we have harmonized data at image level and feature level. So hopefully that paper that I was talking about earlier is going to be published sometime next year, early next year, which sort of goes into much more detail about these different harmonization procedures. And actually, it's a really nice paper in that it sort of compares all of these harmonization procedures against unharmonized data to look at which are the most useful. I think sort of what we found was that it depended on the type of analysis you wanted to do. So there wasn't a sort of clear, as you would expect, there wasn't a sort of clear winner amongst these different harmonization approaches. It very much depended on how you were analyzing the data. But yeah, so hopefully more to follow on that soon when that paper is published. Our data access procedure. So I always kind of put this one in. So this is for anyone wanting to access Psy ShareD data. So as I explained, you sort of visit our website, you view the catalogs. We're hoping to get our catalogs on DataMind, which is a UKRI mental health platform, sort of data hub. So we're in discussions with DataMind currently about doing that. And it may be that our data is sort of accessed via DataMind in the future as well, but that's to be determined. But currently, you would look at the KCL Figshare catalogs, which Ruba was explaining a few moments ago. You would select your data sets, and then you would submit a data access request form, which is fairly light touch. There's some people in the room who will have put one of those in recently. That's then reviewed by the data management committee, and assuming it's approved, I think we've approved all of them, pending some suggestions for amendments. You then need the data user would then need to initiate a data access contract or a data use contract with King's College, between King's College London and their institution, which is then signed off and agreed by all parties. And we've now got a few of those in place. Probably the sort of most rate limiting part of the procedure. When you're dealing with university contracts offices, you can imagine that sort of slows things down a little bit, but it hasn't been too bad. And then the data is transferred via DataLad. Again, as I was saying, it may be in the future that we do that sort of transfer or access process through DataMind, but watch this space and see what happens. I would highly recommend for anyone putting in a data access request that they read the guidance page. I'm not going to go through these now, because I think we need to push on. But yeah, this gives you a sort of step-by-step walkthrough of how to sort of put together a good data access request. And there are a few constraints. For example, if you're a graduate student, you may want to get your supervisor to be the sort of lead applicant on the data access request, and that's purely for contractual reasons. Principles of data sharing, I think, are also on the website. I'm not going to go through these individually, just to say that all data is anonymized, which circumvents the UK and EU GDPR regulations. And when I say anonymized, I mean truly, they should be truly anonymized in that any personal data no longer exists for these data sets. All data sets are sort of older than 10 years, and there's a few sort of marginal exceptions on that. Most importantly, we have NHS database ethical approval. The reference number is there, which provides sort of blanket coverage until 2030, I think. for the use of these data sets, which is good news for everyone, but particularly for data users who then would not need to put in a local ethics application. Yeah, so I think, that's these slides and the recording, I think, will be put up so you can look at this in more detail if you wish to. I think that's it. So for me anyway, so yeah, the website is a sort of point of contact for both contributors and users. Well, contributors can contact me, or they can just or Ruba or Matthew or any of the Psy ShareD members, and or they can, there's a Psy ShareD email, I think, as well, so they can contact us via those routes. So I'm going, there's a few more people coming in now. Can I, before we move on to the next talk, can I ask if there are any questions? And can you speak? Because I can only see a very limited number of people. So putting your hand up, if you put your hand up, I may well miss it. So any questions? Okay, good. So that was all clear. So I'm going to stop sharing. And I think Matthew, you're up next. Is that correct?
Yep, I'm going to share my screen.
Okay, so over to Matthew.
Okay, great. So let me just make sure this. Okay, great. Can you see that all right, Paul?
I can, yes.
Okay, great. All right, so I'm going to be talking about VBM analysis of data from the Psy ShareD dataset. I'm going to focus on first episode psychosis and schizophrenia. So I want to talk a little bit about the Enigma VBM tool that we use. So you're probably familiar with VBM as an established analysis technique which surveys the brain for volume abnormalities. We developed the Enigma tool for the Enigma Consortium, and the design really enables research groups to analyze their data using VBM in a sort of standardized way, but it also does a lot of comprehensive QC, and it transfers group data, so we don't have to sort of worry about private data privacy issues to a coordinating site. So we've kind of adapted this for the Psy ShareD study. So we do, at the moment, we're using a meta-analytical sort of way of analysis, but having access to all the individual data does allow us to potentially look at mega-analysis and validate some of the methodology of the tool. And just to sort of give you an overview of how it works, so you'll have patients and controls, and that would be within an individual site. And then there's a standardized covariates file which we use, which always has the subject ID, diagnosis, age, and sex of the participant. Then we can have any number of clinical variables sort of appended in further columns. And then the user just selects that data. We've made it easy to run, and it does lots of QC and sensitivity analyses. And then it produces this sort of group data Vox T-map, which we then combine with all the other sites, and then we meta-analyze it on a voxel level using something called SDM. So we're using the same procedure in Psy ShareD, and that's really so that we can because we're using exactly the same procedure, we can then compare to other studies that we've done or are using the tool, or other people who have also used the tool as well. Just to briefly talk about SDM, so that was developed by Joaquim Radua, who used to be at King's College London. He's now in Barcelona. And one of the benefits of SDM is it uses robust family-wise error correction for multiple comparisons using threshold-free cluster enhancement. So this is a non-parametric method, so it's quite robust to violations of normality and so on. So that's a sort of benefit of that. So we published our first study using the Enigma VBM tool in early onset psychosis, and that was published in Molecular Psychiatry in January 2024. So that was undertaken by one of my PhD students, Shijing Si. So we had 15 cohorts, 482 early onset psychosis patients, 469 controls. So what we tended to see is reductions in grey matter volume across the whole of the brain, really, in these grey matter regions. What we do is we show any region that passes correction for multiple comparisons. We do that at 0.025 corrected. The reason we do 0.025 is because we look at the the increases and the decreases. So that's just 0.5 divided by 2. So we tended to see these at quite large effect sizes. So if you're familiar with Cohen's effect size, Hedges G is pretty much identical to Cohen's D. So the values will be the same. It's just a very, very small adjustment. And we saw the greatest reduction in the medial cingulate. So these are really quite large effect sizes in brain imaging data, particularly with structural brain imaging data. And I think there is something I have had people say, oh, you know, make the threshold higher so I can just see one little blob. But I think there is, I mean, I kind of go against that a bit. I think there is a human, you know, we kind of want to have one pinpointed region, but I think it's important to show if there are reductions across the brain that we acknowledge this as well. So I think it is a feature of the illness. We do correct, one thing to say is we correct for control for age and ICV, and we model age as a random effect at the site level. We also saw reductions associated with the dose of antipsychotics. So this is chlorpromazine equivalent doses. So we can do a regression in each site. So this is more powerful than meta-regression because we analyze the data within each site and then combine it. So we saw reductions there, but you can see the Hedges effect sizes are smaller than the case control comparison. So it doesn't explain the difference in case control, but it does show some interesting findings in terms of possible associations with antipsychotic use. So how about the before I just move on to Psy ShareD, I just want to show you some results from Enigma bipolar disorder. So this is just a kind of animation showing what happens as we add more and more data. So here actually we've got Z score rather than Hedges G. So this is the significance of the findings. So as we add more and more data, we expect to get kind of more significant findings. And you can see with bipolar disorder where the effect size is quite subtle, we really need to boost that sample size before we get these kind of robust effects. So in bipolar disorder, the effect sizes are smaller. We also see a characteristic change in the splenium of the corpus callosum in the white matter as well. And this was undertaken by Shane Prakar, who was an MSc student working with me. So that was bipolar disorder, but let's move on to the Psy ShareD findings or the analysis of the Psy ShareD data. So this was the data we included for first episode psychosis. So we had a number of sites. So we're very thankful for the PIs and the teams involved there. We are looking to hopefully increase the sample size a little bit with sites. So we had to miss some sites because they didn't have controls or for other reasons, but we hope to increase that a little bit. So we had about a weighted mean age of around about 26, slightly more males and females, which is often a characteristic of this group. So that was our first episode psychosis demographic data. Just looking at the schizophrenia data as well. So we had a few more sites. We had a number of cohorts. Veena Kumari was involved in, but also from Cambridge, Edinburgh, Baltimore, and Toyama in Japan. So again, we're very grateful to everybody who contributed data there. Slightly higher mean age, as we often expect with established schizophrenia. Okay, so how about the findings? So what did we find in our sort of preliminary analysis? So this was undertaken by Kai Huang, who's a current PhD student of mine, and we saw reduced grey matter volume, quite similar, it's sort of a bit similar to the early onset psychosis, and also a similar effect size, potentially a little bit more sort of stronger effect sizes in the thalamus and insula, and potentially less so in the medial cingulate for this group. And yeah, the sample size is comparable to the early onset psychosis and healthy controls that we saw before. So we also looked at schizophrenia, and you can, I don't know if you can see, but I've had to change the color bar because the effect sizes were so large. So we saw some really large effect sizes here, probably the largest I've seen in any data I've looked across with disorders. So we had a peak effect size of 0.68, which is really quite huge actually for structural MRI data. And again, I should say all of these are corrected for age, ICV, and site. And if I just flip between the two, the scale is changing, but you can see the coverage the amount of regions is sort of increased in the amount of regions, but also the effect size across the whole of the brain is really increased in schizophrenia. We also can look at white matter as well, and what's interesting is the effect sizes are slightly less, and that agrees with the literature. We tend to see in sort of region of interest meta-analyses, but quite a large amount of the white matter being affected. And this is the effect in schizophrenia. Again, we've had to change the scale, so the effect sizes were larger. Interestingly, I'm not quite sure why this is, but the brainstem seems to be affected more in first episode psychosis, which is a surprise. I don't know if that's just we haven't done a kind of interaction here, so I don't know if that would actually reach sort of formal significance different, between the two groups, but that's sort of interesting there. So just sort of flipping between that so you can see the effects. Because we have, when you do a kind of free surfer analysis, you would tend to have about 60 regions max. With voxel-based morphometry, we have 200,000 voxels, so we can plot a nice distribution of the effect sizes. This is early onset psychosis, and most voxels clustered around about 0.2. So these are anything to the right of this line is a reduction in brain volume, and then we saw this peak effect size of 0.54, but most voxels kind of clustering around this area here. A small number of voxels showing an increase, but that didn't reach significance. So we didn't see an increase in any of the findings so far in terms of the formal statistical comparison. But what's quite nice about these distribution of effect sizes, we can look at different disorders. So what I've done here is I've plotted a study we've done in OCD in Enigma. So that was quite small effect sizes, much smaller really than these other disorders. We've got bipolar disorder, which I showed the animation of. Then we've got first episode psychosis here. You'll see that's very similar to early onset psychosis, which is helpful to see that consistency with a slight shift to the right in early onset psychosis, suggesting perhaps slightly stronger effects. Schizophrenia, much larger effect. And what's interesting as well is we can plot it against neurological illnesses such as Alzheimer's. So this is based on quite a small sample size, but you can see this great big shift in the effect size. So you would tend to see much bigger changes in grey matter volume, and probably towards the peak, this curve would continue, and the effect size around about 1 would be around the hippocampus. But what I thought was interesting about this is it showed, for me anyway, I thought there wasn't a very clear dichotomy here about neurological versus psychiatric disorders, which I kind of expect to see. I expect to see a bigger gap between, say, schizophrenia and Alzheimer's. So I think this perhaps points towards more of a continuum, perhaps between neurological and psychiatric disorders, although that's a bit speculative. The other sort of take-home message is it's really a story of decreases in brain volume when we correct for ICV. So there's only very small numbers of voxels showing an increase, and none of those reach formal statistical. They don't sort of come out as significant. So in terms of conclusions, we see robust volume reductions in first episode psychosis and schizophrenia with larger effect sizes in the latter. One interesting question is it because of the early stage, or is it because if we looked at those with first episode psychosis, the ones that developed schizophrenia, would those show the same effects as schizophrenia? So from my reading of the data so far, I think it's probably a bit of a mixture of the two. Another point is the current sample size in the Psy ShareD is large enough to obtain significant findings at quite robust family-wise error correction for multiple comparisons. So that's great, and the sample size can only increase really. We'll also be undertaking analysis of those of clinical high risk, and as well as increasing the sample size, we'd be very keen to obtain some additional clinical data on samples such as antipsychotic medication and clinical severity. So, for example, we could look at the effects of antipsychotics as we did in early onset psychosis. So just to finish with acknowledgements, we're hugely grateful to all these sites that have collected data. When I did my PhD, I collected 25 patients and 25 25 controls, and I was very proud of that. But these are huge numbers, and we're very aware that people have spent huge amounts of time collecting this data. So we're very thankful for that, and all those people involved in Psy ShareD. Paul Allen, Kai Huang, and Mariana and Ruba were both involved in some of the sort of data analysis there. So thanks very much, and I'm happy to take any questions.
Thank you, Matthew. That's a great talk. Any questions? Again, I'm not sure I can see everyone's sort of thumbnail, so I don't know if I'll necessarily see hands, but please just speak if you have a question for Matthew. Okay, Matthew, I was going to ask with you may have mentioned it with the data you were you using any of the harmonized data from Psy ShareD, or was that all unharmonized?
That was all unharmonized, but what we potentially can do is I would be interested in the effects of harmonization, and what we can plot is a map of we get an I-squared metric, which is something you often get out of meta-analyses, which gives you an index of systematic difference between sites, and it would be interesting to see if how that affected the results there, and also does that mean that we've become more sensitive to the results? The reason that we've kept it with unharmonized data is really that cross comparisons between disorders, so that by matching the methodology we can then be sure when we say plot those histograms that we're using the same methodology across. But that would be something I would be interested in doing, and seeing if by modeling because at the moment we're modeling site as a random effect, by having harmonized data, does that allow us to be more sensitive to the case control findings?
Okay, that was a really good talk. Just any further questions before we move on to our next speaker or speakers? I think I can't see anything. If anyone else sees a hand or something, I'm so bad at using Teams, as the rest of the Psy ShareD team will tell you. Okay, I think that's a no then. So thank you, Matthew. That was really good, and and that's really good sort of proof of concept sort of analyses really in terms of using the Psy ShareD data. So yeah, great. That's I hope you get that published soon. So you're thinking of adding a clinical high risk comparison in there as well at some point?
Yeah. So we started with the schizophrenia in the first episode just because there was more data there.
Sure.
But yeah, we'd like to have a look at that as well.
Yeah. I think the CHR is up to about roughly the same as the first episode now. So yeah, you should be able to do something fairly robust. Okay, so thank you, Matthew. I think our next talk, is it Ellie from York? Have I got that right? Is Ellie here?
Yeah, I'm here. Good morning, everybody.
Good morning, Ellie. Nice to meet you. Can you share your screen, please?
Yes, I will do my best.
You see that yet? I think we're getting something. Yeah, brilliant.
Does that come up? Can you see the PowerPoint slide?
We can. Thank you. And so just to say before you speak, Ellie, yeah. So Ellie is at University of York and is working with Clara Humpston, and you're going to present on an investigation of childhood trauma and your pathways to hallucinations. So yeah, please go ahead.
Excellent, thank you. Just to say, it's excellent to hear about the rationale and the history of the Psy ShareD project, and especially exciting to hear some of the projects that are coming out of it. So it's great to be here. Yeah, as you mentioned, I am a PhD student from the University of York. I'm supervised by Dr. Clara Humpston, who is also here with me, and Professor Rob Dudley. We're in the Hallucinations, Thought and Self in Schizophrenia lab. I'm going to talk a little bit about how a project that is just kind of beginning. So any kind of thoughts and feedback would be gratefully received. But it's about how childhood trauma might shape the brain pathways that underlie hallucinations, and how we're hoping to kind of test that and some of the kind of cognitive pathways behind it using the MRI data. So just kind of starting off what hallucinations are and how we've kind of built towards the research question. So from our understanding, we describe them as perceptions or perception-like events that are without an external source. So it could be hearing a voice when nobody is speaking, for instance. And we know that these happen across conditions. So we know they happen in psychosis, PTSD, neurological disease, and indeed in the general population. And for some people, these can be really distressing. They can reduce the quality of life and lead to kind of poorer outcomes. And why look at the impact of trauma specifically? Well, we know that a particularly relevant predictor of hallucinations is childhood trauma. So large meta-analysis puts this at 3 times increased risk of psychosis when exposed to childhood trauma in particular. We also know that childhood trauma exposure is linked to greater severity, frequency, and distress associated with hallucinations in psychosis. And indeed, there's something about the content. So trauma-exposed voice hearers often report more negative, critical, or persecutory content. Sometimes this content will be reminiscent of kind of autobiographical memories, and it suggests that maybe there are some phenomenological differences about the experience of people who are having hallucinations for that reason. So we're particularly interested in cognitive explanations for hallucinations. So this arises from the idea that normal perception is underpinned and supported by a range of cognitive abilities and processing styles, and that normal perception, for instance, requires both the sensory input that's coming in, comparing against expectations or priors on how to interpret that, and that these are anchored in memory and source content in order to make sense of them. And that if there's a different breakdown in one or multiple of these support systems, let's call them, this could all potentially arrive at hallucinatory experiences, but through different pathways. So specifically, the kind of cognitive explanations that we're interested in, one is source monitoring deficits. So normally the brain will tag our own thoughts and inner speech as self-generated. But if that tagging system is unreliable, that can blur the line between internal and external. So we might have a internal monologue thought, like I mustn't forget the milk today, but it might arrive with the same qualities of a voice from outside and feel like somebody is speaking that to us. Similarly, another cognitive pathway is overweighted priors. So perception, we know, is a mix of what comes in through the senses and what the brain expects to hear. And through these expectations or priors, they're normally kind of helpful. They help us make sense of ambiguous input, like hearing our friend call our name across a cafe, for instance. But if the weighting on these priors is too strong, the brain will start to hear or see things that it expects, even if the sensory evidence doesn't support this. And then the final cognitive pathway that we're interested in is that memories are normally time-stamped and anchored in context. And so we kind of have a sense when we remember things that they happened in the past. However, traumatic memories in particular are often stored differently, so it's fragmented, highly emotional, and often stripped of context.
Ellie, I think your mic's just gone muted.
Yeah, I don't know if that was a... Your mic is still muted, can you...
Oh, am I back?
You're back.
Okay, so I said I was muted. Hopefully that's not feedback. Let me, I'll just share again.
Your team's doing its own thing, I think.
I think that's what it is. There we go.
Yep, I think that's what, yep, you just need to, yeah.
Excellent. If I start from here, is that?
Yeah, that's fine. I think that's where you were, isn't it?
Where we start. Yeah, okay.
Perfect.
Yeah, so did you, I sort of spoke a little about the sort of source monitoring account and the overweighted priors account. Did you guys hear that bit?
Yeah, I think were you just mentioning intrusive memories?
Perfect, absolutely. I'll continue from there then. Yes, so this idea about intrusive memories as a pathway towards hallucination stems from this idea that particularly if memories are encoded under traumatic conditions, that these might be lacking in certain kind of contextual tagging systems, which means that they are very vulnerable both to be intrusively experienced and arise into our consciousness, but also that might lack some of the kind of context which helps us remember that these are memories and not kind of happening presently. And this kind of stems from PTSD literature. So the idea is hallucinations can emerge through multiple different breakdowns, not from a single mechanism necessarily. And this kind of brings us on to why we might be particularly interested in looking at whether the pathways might be different for people who have or haven't been exposed to childhood trauma. So one kind of proposed pathway linked to trauma exposure might be that it is driven primarily by intrusive memories, poor contextual integration, and dissociation. And these rely on circuits such as the hippocampus, the amygdala, the medial prefrontal cortex, the anterior cingulate. Trauma, we know, alters these circuits and potentially leaves them a little bit more vulnerable. In people who haven't or have experienced significantly less exposure to childhood trauma, potentially the cognitive biases that are driving their hallucinatory experiences might be things like source monitoring deficits or overweighted priors rather than a kind of memory mechanism. And these rely on perceptual and monitoring circuits involving areas like the superior temporal gyrus, Heschel's gyrus, dorsolateral prefrontal cortex, and temporoparietal junction. And the idea, importantly, is that whilst all these routes might lead to hallucinations, the phenomenology might be a little bit different. So, for instance, trauma-related hallucinations may have more of a ties to memories and past experiences, whereas non-trauma hallucinations might be a little bit more linked to perceptual experiences, unfamiliar voices and sounds. So if different pathways exist on the cognitive level, this should leave different signatures in the brain, and that is why structural neuroimaging is particularly helpful to us here. And in particular, we're interested in kind of mapping on these different cognitive pathways into whether we can see differences in circuits, and particularly if exposure to childhood trauma is biasing which pathway is driving hallucinations. So just briefly, some of the literature that emerges when you look at kind of PTSD literature and trauma literature more generally. Pretty robustly, we see reductions in hippocampal volume. The picture is a little bit more mixed when it comes to the amygdala. There's some suggestion that it might be increased in youth and reduced in adults. We see thinner cortex and reduced volume in the medial prefrontal cortex and the anterior cingulate, and also altered connectivity in the insular and salience network. It also importantly seems like timing is important here. So earlier trauma seems to be a little bit more linked to affecting the hippocampus, whilst later tends to impact prefrontal regions. And then briefly on the hallucination literature, there's a slightly different pattern. So the most consistent findings tend to be reductions in the superior temporal gyrus and Heschel's gyrus, particularly in persistent auditory verbal hallucinations. Dorsolateral prefrontal cortex linked to monitoring and executive control. And in the temporoparietal junction, differences that we see linked to self-other misattribution. And in general, larger meta-analysis seem to point to consistent perceptual monitoring deficits. For the project, we're hoping to use structural covariance network analysis. The reason this is useful is it's common for studies to look at single brain areas, but the brain works largely as networks. And structural covariance asks whether two regions vary across people. So, for instance, do people with small hippocampi also tend to have thinner prefrontal cortices? And if so, we might conclude that those regions likely adapt together and develop together as a system. This is likely reflecting shared maturation, experience, genetic influence, and provides a little bit more of a higher level network perspective on the brain and what might be different in the brains of people who have experienced childhood trauma. And it's important and useful to look at here because we know that both trauma and hallucinations disrupt distributed circuits, not just isolated areas. And PTSD research shows that covariance patterns in visual and limbic systems predict these intrusive memories, whilst in schizophrenia research, we can see that disrupted frontotemporal covariance is linked to hallucinations. But to our knowledge, nobody has used as yet structural covariance network analysis to stratify people who hallucinate by trauma exposure. So of course, we're not quite sure what we'll find, but some kind of suggestions might be that we see people who have experienced trauma having additional thinning in the hippocampus, medial prefrontal cortex. People who haven't experienced that, there are more notable changes in thinning in STG, Heschel's gyrus, and dorsolateral prefrontal cortex. And so essentially whether we have what looks like more of a memory emotion change signature or a perceptual monitoring change signature. And And the idea is potentially we might see something kind of approaching a dissociation between how trauma exposure is shifting the cognitive bias and therefore the kind of structural brain patterns towards slightly different routes towards the hallucinations. So formally, our hypotheses at the moment are that in trauma-exposed hallucinators, we're expecting to see additional thinning in the hippocampus, amygdala, MPFC, ACC, and stronger hippocampus MPFC covariance. And in people with less trauma exposure, more so thinning in the STG, Heschel's, gyrus, dorsolateral prefrontal cortex, and stronger STG, dorsolateral prefrontal cortex covariance. And then just to touch on kind of why we hope this matters, we think that if trauma biases which pathway drives hallucinations, it could help us explain why hallucinations might feel quite different across people. We mentioned that trauma-related hallucinations often are quite emotionally intense and autobiographical, whereas non-trauma related is more perceptual or perhaps related to unfamiliar voices. And there might be possible treatment implications from this. So if we can kind of reliably find differences in cognitive mechanisms reflected in structural pathways in the brain linked to childhood trauma exposure, it might be informative as to whether therapies which target more memory and emotional regulation might be more effective, as opposed to things like perceptual retraining or monitoring-based strategies. Okay, so just to summarize, childhood trauma alters memory emotion circuits, hallucinations seem to involve perceptual monitoring circuits, and we're interested in how trauma might bias which pathway is most disrupted. And stratifying people who hallucinate by childhood trauma exposure and using structural covariance lets us test these network level differences. So we're at the very beginning of this project, but we're very excited about it. We'd be really keen to hear any thoughts or feedback. I'd welcome any questions, and you're welcome to reach out to me or Clara by email. And just to briefly acknowledge, obviously my supervisors, Dr. Clara and Professor Rob Dudley, who have been excellent. A huge thanks to the Psy ShareD network, who, especially as an early career researcher, it's been incredible being able to access this as a resource, and the University of Psychology, the University of York Psychology Department, which is funding my PhD. So thank you very much.
Okay, thank you, Ellie. That was a great talk. Any questions for Ellie before we move on? And again, please speak.
Yeah, I have a question. This is Sophie Frango. Thank you very much for the presentation.
Hi, Sophia. Go ahead.
Hi. I was just wondering why childhood trauma? People can have trauma later on. That how are you thinking about that? That's the only thing.
Yeah, absolutely. That's a really important point. I think it's something that continues to be because the PhD more broadly is around childhood trauma. The reason that it becomes a little bit sticky is that obviously that we know that people experiencing hallucinations, and particularly if people are involuntarily kind of having treatment or in hospitals or things like that, because of that in itself compounds trauma and creates trauma. There's lots of very interesting literature about how later in life trauma compared to childhood trauma might kind of look different, but it can be a little bit difficult to untangle kind of later on in life the influence of trauma itself and the influence of kind of ongoing trauma. And I think when it comes to the questions that we're asking, there does seem to be something about childhood trauma in terms of like kind of developmental sensitivity windows that seem to be quite important for shaping some of the cognitive routes that are proposed, and potentially also some of the structural brain signatures that we might see. So we've kind of, not quite arbitrarily, but we've kind of consigned it to that for both the sake of trying to keep the question a little bit more focused, and also because it might link to the cognitive pathways. But it's definitely something that would be interesting to think about in other and future research, what that kind of, as you quite rightly says, trauma is something that in many ways will continue to kind of impact people and therefore impact the brain and therefore impact cognitive pathways as well.
Okay. Okay, thank you, Ellie. Yeah, I can't remember the CTQ it's a while since I've used it, whether you can, is there a dissociation between sort of really early childhood trauma and sort of later trauma up to your into sort of adolescence? I can't remember whether it measures it in sort of different stages. So that might be something that you can, or different developmental stages. I think that might be something you can look at. But yeah, I mean, I think one of the constraints, obviously, with Psy ShareD is that we are working with retrospective data, so you can only sort of work with the data that is there. But yeah, and I really like the idea of this idea of multiple mechanisms for hallucinations that may come about through different sort of causes, sort of trauma versus non-trauma. I think the predictive coding guys wouldn't like that account, so be careful who reviews your paper. But yeah, I think it's quite intuitive. Any other questions for Ellie quickly before we move on to our next speaker? Okay, I'll take that as a no then. So thank you very much, Ali. That was really good. I think Anping is our next speaker. Anping, are you here in the room? Can you share your slides?
Yes. Hello, everybody. I hope you can see me.
We can. Yes, we can. Yes.
Okay. Okay.
We can see the top half of you, top half of your head. That's
Okay,
fine. So
sorry.
we just need to
Okay.
see the slides though. That's the
Okay.
and which we can now. So please go ahead when you're ready.
Yeah. Let me just find my slide.
So
Okay.
Anping is working at the Institute of Science Tokyo. Anping's application with Genichi was approved, I think, recently. I can't remember exactly when. So yeah, let's hear a little bit about your project.
Yeah. So our project is identifying subtypes of cortical sickness in schizophrenia. So I'm gonna start by introducing our study aim. First is to use a variational autoencoder, VAE, to discover the latent patterns in cortical thickness data of schizophrenia samples. And we hypothesized we could probably find 2 to 3 or more distinct subtypes based on prior studies. And next, we're going to find to generate the cortical thickness maps for each subtypes we find and identify the key differentiating ROIs. And finally, we're going to examine whether the identified subtypes would differ in clinical characteristics, where mainly we're going to use the PANAS scores. I'm going to introduce briefly about VAE. So the VAE we use actually we use the encoder, VAE encoder, to learn features from the input, which is normally 2D images, using some dimension reduction techniques. And then the VAE decoder will reconstruct new images by sampling from a unit Gaussian distribution from the vector it learned. So the reconstruction of the new images is used mainly for generalization purpose. But in practice, there is a trade-off between the reconstruction accuracy and the generalization of the new images. So the main thing we do is to fine-tune the VAE parameters, mainly the beta, that there's a beta thing in the VAE model. We fine-tune the beta to find the model that gives the best performance. Yeah, but before we do the VAE training, we do a thing called geometric reformatting, which is process all subjects' 3D cortical thickness data into a standardized 2D images as the input to the VAE. Currently, these are the data we have from different sites. So after the 2D transformation, we did neural comeback to remove the site effects. And after the neural comeback, we feed the 2D images into the VAE. And after fine tune, we find the best performance is at beta equals 14. So here is a summary of the reconstruction performance at beta equals 14. And the average expanded variance is the thing that values. So these numbers actually means the VAE captures more than 60% and nearly 70% of the original data's variability. So here is a visualization of the VAE reconstruction performance, all normalized. And you can see all left sides are the original images and right side are the reconstructed images. And you can see the model actually capture the most important features, like nearly 70% of the original images of different subjects. And now after the reconstruction thing, we are trying to build some subtyping analysis pipeline before we receive more data from ShareD. So here is a visualization of the GMM clustering. I choose 2 to 7 group subtypes of the VAE learned representation of each subject. So you can see each dot represent each subject's learned vector in the latent space of VAE in 2D dimensions UMAP. Because now we're building the pipeline, so I just choose 7 clusters to do further analysis. And I reconstructed the 3D prototype of cluster 1 and 4, also subtype 1 and 4, because the distance between 1 and 4 is the longest. So you can see the prototype of 1 and 4 is actually pretty different in terms of cortical thickness. So after this, we're going to do some subtype analysis. So our plan was to first identify the key differentiating ROIs across all subtypes, and if there are any significant ROIs, they could probably serve as potential biomarkers. And secondly, we're going to assess whether the subtypes have clinical meanings. So we're going to use the panel score. And lastly, we're going to bridge the ROI findings and the clinical data to find if there are any interactions between these two. Yeah, thank you. I think so far this is our plan.
Okay, thank you, Anping. That was very, very concise. Can I just before I open up, can I just ask with the Psy ShareD data, and I would have read this, but it's are you going to use the Psy ShareD samples to sort of increase the sample size of the analyses that you've already run, or are you going to use them in some sort of validation or independent data set sort of validation approach?
Yes, the first one. We're going to add the ShareD data into our existence stuff.
Okay.
Because right now our sample size is small. We only have like 300 people. We think it's not enough to find features that is like could give strong evidence about the subject. Yeah.
That differentiate clusters and potential different sort of diagnostic or prognostic. And of course having I don't know how much outcome data you have in your existing sample or how much there is in the Psy ShareD samples you requested, but looking at maybe sort of outcomes as well, if they're predictive in that way, might be quite interesting as well. Any other questions, Anping, before we move on to Ruba?
I just had a brief question. Thanks for your talk. It was really interesting. The methods you used, I hadn't come across before, but I'm just wondering, has it been successfully used in other disorders where there's like, I don't know, a large sample size in Alzheimer's or something, or is this the first time you're applying this to neuroimaging data?
It has been used in because I use the VAE to study the cortical thickness, but before this, people has been used this to study the fMRI, like the signal data. So this might be the first time on cortical thickness, but yeah, the 2D images and input are the same format.
Okay, great. Thank you. No, that's really interesting. Thank you.
Okay,
can I?
Oh, sorry, yes, Sophia. Yes, go ahead.
Is there time for a comment?
Yeah, I think yeah, one quick one.
Yeah, so I think this is a really nice new approach actually to subtyping. It hasn't been used before in schizophrenia. There is a paper that we just summarize all the subtypes based on neuroimaging data that have been published in schizophrenia that is coming out in biological psychiatry sometime in the beginning of the next year or the end of this year, if anybody wants to go and have a look at it. But my comment here is actually about the issue when you do this really is, and I didn't kind of quite understand how did you address variance that is sort of associated with age and sex versus variance that's associated with disease. I didn't get that.
I plan to regress out to use age and sex as covariance when I do the analysis. I plan to regress them out as covariance.
So the subtypes you showed are not corrected for age and sex.
Yes, because I had two options. The first one is to regress them out before do subtyping. The second one is after do subtype, I regress them out as covariance. When I do analysis, I choose the second one. Because I
You
think
have to
if I
choose the first one. No, you have to do the first one. It's my very strong recommendation.
Thank you.
So remove and then in your controls, you actually just do your U maps again to see whether you have successfully removed site.
Okay. Thank you. Thank you very much.
A couple of suggestions. You're welcome.
Sophia, are there a couple of papers you could, or papers you could put into the chat that would be helpful for anything? I know, like a lot of the Centaur brain stuff that you've published, and certainly that's quite relevant to the sort of variation in age. I don't know if there's anything you could recommend for Anting to read.
I think our subtyping paper is somewhere in BioRx. I don't have the link with me, but I can perhaps share it afterwards.
Yeah,
I'll try and find it while we're talking and put it in the chat.
Yeah,
but
just send them to me and I can pass them on.
Doesn't actually use the auto recorders, but we have actually tried to use them, and we use the conditional variation auto recorders. It doesn't actually matter that much now. But one of the things that I wanted to share here is that the number of subtypes is very, very sensitive to age and sex and chronicity distributions. And it's also very sensitive to sample size. Yeah. So things to be careful about. But in the first instance, I think looking at your controls and making sure that your reconstruction is independent of site by just doing again your T2D U maps, yeah, and to actually make sure that you're not simply capturing non-specific variation in disease that is associated with site that is independent of age and sex, but you have to regress age and sex before the subtyping. That's definitely something you need to consider very, very seriously. Yeah, that's it.
Thank you very much.
Okay, thank you, Sophia. And I think and this is really important that particularly with more junior researchers who are taking on these studies and these projects, that to be able to sort of get access to this kind of sort of advice in terms of analysis. And I think that's something that is important to Psy ShareD. That's I don't know if mentoring is the right word to use in that context, but yeah, that sort of mentoring for junior researchers. So look, Sophia, if you can put some links and just
harassing junior researchers, you mean?
To me, then I can pass them on to Anping, or if you get time, put them in the chat. We'll work something out. We better move on to our next speaker, which is Ruba. So Ruba, are you able to share your screen?
Yeah. Good morning, everyone.
Hi, Ruba. So Ruba's been working on the project. So Ruba knows Psy ShareD very well. Has been working on the project for over 2 years now. Has been instrumental in all the sort of organization and processing steps that we've implemented, and is going to talk about her analysis this morning. I think is this for your PhD? It is, yes.
Yeah, so I have been doing my PhD since last year here in with King's. My main focus is like it's a bit different. It's research, reproducibility, and data integrity in neuroscience studies. As a part of the project, I am creating a case study for my original project. So for the case study, I'm using Psy ShareD data, and my project actually focuses on developing individualized approach to understand the brain alteration during psychosis disorder. So the title of the project is using perturbation network analysis for of structural T1 MRI data in psychosis. So it's very early stage right now. So I'm just sharing my research goal and how I'm um, planning to complete it. So we all know like psychosis spectrum disorders like clinical health, high risk and fast episode psychosis show huge heterogeneous changes in brain. And while most of the cases, the abnormalities we saw in frontal, temporal, or striatal regions, but only 7% of patients actually shared the same affected areas. So, but traditional neuroimaging studies, they mainly focus on the group level differences, but it limits the clinical utility for individual level deviations. That's why in this study, I'm focusing on network-based approaches because they more targeted the individual level deviation rather than the group averages. Existing literature shows that these network-based approaches still have lackings because of the small sample size, single set designs, and this stuff. And so I thought Psy ShareD is Psy ShareD is an opportunity because we are collecting data from different sites with different ethnicity and different regions. So it gives a huge data set, and I thought we can utilize it for this problem. So in this study, we actually propose an integrated statistical and AI framework that will utilize this T1 MRI data set with explainable machine learning and a perturbation covariance analysis to bridge the gap between group level findings and individual biomarkers to create a more precise tools to understand to detect the early treatment and early detection to help with early detection and the personalized treatment procedures in psychosis. So this study mainly focuses on three main goals. The first one is to identify the different brain regions that mainly influences the psychosis disease in different stages. Mainly, initially, I'm focusing on the clinical high risk and the first episode psychosis. And the second goal is to using those regions to identify how those regions actually connected and they influence and interact at individual levels for these two groups, healthy control CHR and FEP group. And lastly, to link the baseline network that we generate from the second study to see how they actually uh, uh, identify the deviations for the treatment response and the symptom trajectory. These are the three main goals for this project actually. So for the study design, I'm using mixed cross-sectional and longitudinal data that's actually coming from Psy ShareD data, and I'm mainly using free surfer-derived brain regions as well as the demographic and the clinical measures that's available for those particular data set. In the data analysis, as I say, there's three main goals. I'm actually focusing on three different uh, uh, three different approaches to identify these goals. The first one is to identify the brain regions. So for this, I'm actually using machine learning models to classify these three groups and then use the explainable AI that can actually identify like which regions are mainly contributed for differentiate among these groups, the CHR, FEP, and HC group. And once I have all the brain regions ranked, that will be used as the input for the second study. In the second study, the goal is to use these brain regions and create perturbation network analysis to see how they are actually connected for the CHR, AFP, and HC group. It's mainly focusing on the creating subject-specific developing subject-specific network group to see how these regions actually changes in these particular stages. And the third one is to we will use the subset of APP group from the second study, both baseline and the follow-up data, and use this subject-specific network group to see how they actually, if this network actually can detect the differences between the treatment response and non-treatment response in the AFP group. And in the third study, the second goal is to identify how antipsychotic medicine actually influence in the AFP baseline and the follow-up group. So yeah, that's the plan of the data analysis part. And for this, I have collected data from 15 different I'm using 15 different data sets from Psy ShareD consortium. These are actually coming from 5 different countries. And as you can see, almost there is like 1,500 data overall data set. And among them, like more than 600 data is for healthy control. 400 around 450 data set is for say clinical health risk, and yeah, same sort of data for the AFP and AFP follow-up group. And there's some data description that I did for sanity test. Actually, I said it's very early stage, so it seems the data set that I'm considering for the analysis, the healthy control CHR and AFP group more balanced, I would say, for the analysis. So I'm expecting that it shouldn't be problem with the imbalanced data set for the first study goal actually. And the data distribution, age distribution per group, it seems the CHR is the most youngest group in this data set, and the AFP is the most oldest one, and the HC in between of this data set. And these are actually I did for the data sanity test, and it seems the literature, it's the male brain volume supposed to be larger than the female, and throughout the data set it's actually shows the same. This is also the changes of total gray matter with the ages across 3 different participants. It shows that AFP group actually shows a sharp decline, where CHR is a bit higher than the healthy group. It might be because of the data set, because I told you that the CHR group is more youngest one, maybe that's why or something. So I try to regress out the result, regress out the effect of the sex and also the head size, the intracranial volume. And after doing that, it seems the pattern of these 3 groups actually changed a bit. The AFP is still the lowest one, but CHR also actually kind of similar with the healthy control group. And so, yeah, that's all basically. It's I told you that it's very preliminary stage, and I'm still trying to develop the model that can actually help me with the fast study. Yeah, that's all. Thank you. Thank you for listening.
Okay, thank you, Ruba. Any questions?
I have a comment again, if I may.
You may.
Yes.
Go ahead.
Thank you. So thanks for the presentation, of course. I just wanted to clarify something. So the first step in your analysis is essentially to use some sort of explainable AI to derive essentially group level ROIs that differentiate between controls and first episode patients, say.
Yeah.
Correct?
Yes.
And then you will use these ROIs to do the individualized network perturbation analysis. Is that correct?
Yes.
So there's a slight thing that you might want to consider here. So at the individual level, there is very little consistency with the group levels. So people have individual changes that are not necessarily captured. So your group level analysis will really capture a minority of ROIs that have the most significant contribution, but that doesn't mean that these ROIs are also present in each individual.
Okay.
So you might want to think a little bit more how you move from the group to the individual analysis.
Okay.
And whether these two aims should be separated. So you can have one aim and say, these are the ROIs that more at the group level seem to be more significant in discriminating, but the individual maps may need to separate.
Yeah, definitely. Thank you.
Thanks, Sophia. Yeah, I think that sounds very very sensible advice. We may want to look into that a bit more, Ruba. The other thing I was going to say as well, in your clinical high risk group, I think for longitudinal follow up, I think you did just look at your numbers again. Where is it? Yes, this one is that the yes, yeah. I think you for the follow up that there should be more scans than that. It just depends whether you have the associated link data you need, but we may want to look at that again and just to check those numbers are right.
Yeah, I will, because we talked about it, and I should change.
Yeah, there's some confusion in some of the way that data is catalogued, isn't there? I think we should probably try and sort that out actually, because if it's confusing us, it will certainly confuse external users. Okay, thank you. I think that's a really good presentation, and I think that's the end of the 4 data user presentations. So thank you to everyone who's presented on their projects. So I think that brings us to our final presentation, which is Jack Rogers from Birmingham, who's going to talk a little bit about sort of future plans for Psy ShareD and developing tools, toolbox. Are you with us, Jack, still?
Yes. I am.
Yep. Okay, great. When you're ready.
Excellent. Let's just get set up. I think my computer froze there, Paul. Sorry. Can't hear you, sorry, Paul.
I'm on mute. Yeah, we can see this. Oh, there we go. All done.
Okay. Thank you. Sorry about that. Great. Thanks, everybody. And thanks to everyone for talking about the projects that the people are engaged with. So I'm going to talk a little bit about some potential research approaches. This is by no means exhaustive, and potential next phases, I suppose, next steps for this work. So apologies for people that were at SIRS in Chicago Chicago earlier in the year. There's a bit of overlap with some of the work that we discussed as part of that symposium. So essentially, how we could maybe leverage Psy ShareD data resource to develop new open access tools, build on obviously analytical approaches that already exist, to try and develop approaches to early outcome detection within the Psy ShareD database, think about stratification, explore different phenotypes, and also develop pipelines for open access use. So Matthew talked about the Enigma VBM tool, thinking about what Paul was saying, obviously in terms of leveling up, having people access globally to the Psy ShareD database, and also different stages of people's careers. So in no particular order, one sort of approach that we've been exploring a bit is brain age. So there is evidence to show, established evidence now to show that advanced brain age or increased brain aging has been observed across different psychiatric disorders. Particularly with evidence showing that these can be present in early stages of illness, so including at clinical high risk stage, at risk mental state. What's interesting is that a reduction in grey matter volume is one of the more established patterns of advanced or increased brain aging in psychosis, and this is often greater than in other mental health disorders. And whilst the evidence is mixed, certainly there's demonstration that around on average there's around a 5-year age gap between sort of chronological age in the patients and computed predicted brain age, so a sort of brain age gap between chronological age and the individual's brain age. One of the challenges and limitations of brain age modelling is sort of, I suppose, thinking about what it adds over and above looking at differences in brain structure, grey matter volume, which we know is well recognised in psychosis. So what's the sort of mechanistic insights that brain age can offer, and how that might improve, I suppose, thinking about causation over and above just looking at the association with sort of changes in grey matter volume. One area that we might explore is thinking about other aspects of things like neurotoxicity. So work from our group and from a number of others suggests that people with psychosis have increased oxidative stress, so increased neurotoxicity, reduced oxidative defense, and particularly associations between reduced oxidative defense and increased brain age. So that's one area that we've been exploring recently, and something that I think, potentially, as we add additional data to the Psy ShareD database, we could potentially explore as well. So this is data using the Benjamin study, so the benefits for minocycline study and spring data from with colleagues around the UK. This was work led by Alex Murray, who is a PhD student working with Rachel Upthegrove and I. And what we really wanted to try and explore is whether biological aging, brain aging, might be related to brain structure, so as people have shown previously, but also potentially looking at associations with other neurometabolites linked to oxidative stress. So we conducted brain age prediction models using people with different stages of illness, so first episode psychosis, more established schizophrenia, compared to controls. This was using 2 different brain age models, brain age R, which we've been using as part of the Psy ShareD database already, so Mariana's been exploring that as well as some other algorithms, and SG Boost, which actually Ruba just alluded to in her presentation. What we found, which was good as replicated previous findings, I suppose, is that particularly for the established schizophrenia group, there was increased brain aging compared to those with first episode and high healthy controls. We also explored what's called Shapley's additive explanations, which in Ruba's talk, when she talked about the explorative AI approach, is basically a means for identifying particular features from within the structural MRI data that might be driving things like differences in brain age. And we found that actually ventricular enlargement as well as total grey matter volume was driving feature prediction within these particular models. So replicates obviously a lot of work showing that grey matter volume differences exist in different stages of psychotic illness. This is work that's soon to be submitted to Schizophrenia Bulletin. The other thing we showed within this data, which was quite novel, was that Alex also explored associations in terms of predicted age difference, so associations with brain age across the clinical groups with different neurometabolites, different changes in biomarker features that we had within our data, in this case using magnetic resonance spectroscopy data. And what was interesting is that the biomarkers that particularly correlated with brain age were total acetylaspirate, so TNAA, and glutathione, markers that have been shown previously to be important in impacting on oxidative stress in the brains of people with psychosis. We didn't find any associations in the healthy control group, and we didn't find any associations with some of our other metabolic and blood-based markers. markers. So our group is also particularly interested in the role of immune-related response differences in pro and anti-inflammatory state within psychosis. But what's interesting and meaningful is that we did find associations with key measures of change in neurometabolites within the brain associated with brain age differences. And what this suggests, tentatively at least, and obviously needs to be replicated in larger samples, is that advanced brain age and schizophrenia may be related to illness severity. So we also showed some associations with the PANSS score, positive and negative symptom scale scores, as well as potentially poor defense against oxidative stress. I should say that we controlled, as alluded to in other comments, we controlled for the effects of age and age squared. And also there was no association with antipsychotic medication dose nor lifetime medication exposure in this sample. Another area that we're particularly interested in is obviously expanding some of this approach to think about neurocognition. So that's data that we also have within the Psy ShareD database, as well as potentially looking at different metabolic markers, as I alluded to in the previous slide. So a nice review a number of years ago now, Franco and Gazer, that cites other data, talks about significantly higher brain age scores around 2.5 years reported in people with schizophrenia spectrum disorder, but not those with bipolar disorder. And you can see that in this image here. But interestingly, that was linked to grey matter volume changes and also metabolic factors. Particularly in this case, looking at associations with obesity and body mass index within the sample. So what we're showing is that a diagnosis of first episode schizophrenia and comorbid obesity, when added to the brain age model, resulted in the highest brain age scores in this population compared to those with first episode psychosis without comorbid obesity, and was lowest in those in the healthy controls without comorbid obesity. So this suggests that potential associations with brain age, psychiatric diagnosis and other metabolic factors might be interesting, particularly when thinking about targeting physical health as well as mental health, and might also be underpinned by changes that we know to be important around things like insulin signaling, neurometabolic changes associated in the periphery with glutathione and acetyl aspartate, for instance. The other area that is of particular interest that we could explore within the context of the Psy ShareD database is building on known differences in grey matter volume linked to patterns of cognitive impairment, as well as neuroprotective factors that have been shown in individuals with schizophrenia. So this was work done using a clustering approach, highlighting differences in grey matter volume in different populations and associated with different changes in things like cognitive impairment. So what this suggests is that we could explore within the context of the Psy ShareD data protective factors such as cognitive reserve, the impact on IQ that might slow or negate things like brain age changes in schizophrenia and spectrum disorders, and obviously at the moment these sorts of neuroprotective factors aren't well understood. This is one that nicely Mariana has been working on as part of the Psy ShareD database already, particularly looking at sort of data harmonization. And this is work that Paul referred to, a paper that's currently under review at Human Brain Mapping, applying different brain age models to the data, including Brain Age R, sort of Iguana, as well as HACR3. In this case, looking at differences in negative and positive symptoms. So that work is currently under review. Another approach that we've been considering, and that I know a number of others have used, is thinking about sort of more cluster-based approaches, machine learning models. So thinking about supervised, unsupervised, or semi-supervised in reference to control groups, machine learning models trained on clinical as well as neuroimaging data, to really try and explore heterogeneity, comorbidity, prognosis, and links to onset of illness. Some of these analytical approaches are starting to be applied to the Psy ShareD database. So this is work conducted by Paris Elusis, formerly at Birmingham, now at King's College, using the ProNEA database, which also forms part of the Psy ShareD database. I believe certainly the Birmingham data, I think, is part of it. In this case, using a tool called NeuroMiner. And what Paris did was to basically use this classifier to try and dissociate those defined as having pure recent onset psychosis, which is the blue blobs here, with those with pure recent onset depression. And did this across clinical and neurocognitive data, as well as looking at differences in grey matter volume. And really to try and look at shared as well as distinct sort of illness features at the phenotypic level, as well as at the brain-based level, that may help inform things like more precise differential diagnostic models. What was interesting about this work as well is obviously, so the model, the classifier did a good job at separating the two different populations. But what's also interesting is there was a shift of the comorbid patients towards the depression phenotype. So basically what that says is that people with depression and or comorbid depression, whether that be a recent onset psychosis, recent onset depression, tended to sort of group more closely than those with pure, what's defined here as pure recent onset psychosis. And that was observed at both the clinical and biological levels, showing differences, increases and decreases in grey matter volume. And so obviously this is something that we could explore within the context of the representative Psy ShareD data, and thinking particularly about how these sorts of approaches could develop, sort of group level, as well as potentially more individually stratified therapeutic intervention approaches within the data. Another approach that both Paris and Alex, who worked with us, have been doing on a number of different data sets has been applying another semi-supervised model, machine learning model called HYDRA, or heterogeneity through discriminative analysis. This is a tool that I know some people have different views on in terms of how, I suppose, accurate and efficient it is. What HYDRA does essentially is to separate patient samples from healthy controls by forming what's called a convex polytope classifier to try and identify different disease-specific subgroups, which is why it's referred to as sort of semi-supervised. So the subgrouping is relative to healthy controls. Here within the data, heterogeneity is disentangled by clustering using adaptive form of k-means clustering the clinical samples from the healthy controls using different linear and non-linear subclassifiers. And so Paris has used this work again to look at classifying patients with recent onset psychosis versus depression relative to healthy subjects, and looking more at disease-related heterogeneity, particularly within structural MRI data, and found quite clear significant differences in brain structure within these different populations, and you can read that work in biological psychiatry. We've also been applying HYDRA in a slightly different way, here identifying different inflammatory subgroups. So I won't go into too much detail about the different types of inflammatory markers, other than to say that HYDRA did quite a good job at identifying 4 different patient control clusters. This was independent of stage of illness, independent of age and site as well, although BMI was a factor, which relates to what I alluded to earlier about different metabolic profiles. So we found things like an increased C-reactive protein cluster, an increased interleukin-6 cluster, so these are different cytokines within the blood, tumor necrosis factor alpha cluster, and what we called a non-inflamed cluster. And essentially what this let us do is to then generate these different inflammatory subgroups, and then explore differences in brain structure within the context of these different subgroups based on the HYDRA response. And one's worth noting is that for our CRP group, there were most widespread grey matter volume reductions and greatest cognitive deficits as measured using things like the IQ testing, which we also have within Psy ShareD, as well as things like reading testing and NBAC tests. For the interleukin-6 cluster, we found they scored highest on the PANS, the positive and negative symptom scale, particularly on the anxiodepressive dimension, and there were overlapping as well as distinct grey matter volume reductions within regions of the brain, including left superior frontal and inferior temporal cortex, as well as things like a non-inflamed cluster, so distinct grey matter volumes within within this subgroup, which might relate to a different treatment response profile within these individuals, those that might respond to more traditional treatment approaches, antipsychotics, for instance. So what I'm suggesting with this data is essentially we're able to use a novel machine learning algorithm to identify different subgroups with different profiles, whether that be neurobiological profiles, in this case inflammatory profiles. We could also think about clinical and cognitive outcomes within the context of the Psy ShareD database. Another area that we've explored in the past is thinking about genetically predicted changes in brain structure. So this was work conducted a couple of years ago by Jackie Williams, formerly at Birmingham, now in the US, in this case using UK Biobank data. In this case, what we did was to build on our work looking at different inflammatory responses within the brain in those with schizophrenia. Here looking at genetically predicted levels of these blood-based markers like interleukin-6 and how that might be associated with grey matter volume within key regions that have been implicated previously in schizophrenia, including middle temporal gyrus, inferior temporal cortex, fusiform, frontal cortex, particularly in this case looking at cortical thickness. And so essentially it was hypothesized and subsequently found that genetically predicted levels in this case of inflammatory markers were associated with changes in grey matter volume and cortical thickness in areas highly relevant to schizophrenia, as well as other neuropsychiatric disorders. So what would be really nice in the context of obviously the Psy ShareD data is to think about then how we could use large data genetic and GWAS studies, so genetic wide association studies, to think about how genes overexpressed within particular brain regions might be linked to biological processes which underlie the pathology of schizophrenia and different stages of psychiatric illness. The final work I'm going to talk about today is work that's formed part of the Enigma project, which Matthew and others mentioned today. So here as part of the Enigma Clinical High Risk Working Group, people have explored things like changes in brain morphometry. So particularly it's been reported that there was lower cortical thickness, but not cortical surface or subcortical volume, which you can see in grey here, was more pronounced in individuals at clinical high risk. And that these changes in cortical thickness were associated with age and can also be linked then to underlying things like brain age modeling, as I talked about before, and potentially linking to different metabolic processes. So the key finding here, using effect sizes, obviously consistent with the sort of work that's been done in terms of the meta and mega-analyses within Enigma, is to compare with healthy controls. Individuals at clinical high risk had lower cortical thickness across the cortex, which you can see in the sort of red and pink colours. Those that were not significant are shown in grey. They also report lower cortical thickness within superior temporal areas and fusiform regions, which we've also found, as I mentioned in the previous slides. Another approach that's been taken is to think about normative modelling in different areas of the brain using Enigma data. And here attempts to quantify deviations from the normative range in different phenotypes, here in individuals at clinical high risk, to basically try and evaluate their overlap or the lack of overlap, if you like, within this sort of distribution, and potentially their association with positive symptoms, cognition, conversion to psychotic disorder, and ultimate prognosis. So here, actually, within a recent case control study, the variation of neuroanatomy in individuals with clinical high risk was nested within the normal range, so there was no difference compared to controls. But obviously, that's something that warrants further exploration, and other normative models such as centile brain, which Mariana started to explore. Sophia has mentioned as well. So obviously, something that we could do with the larger representative sample that is well characterized and using the raw data rather than looking at things like effect sizes. So essentially, what I've been talking about today are some potential ways, I think, to develop more refined models that could allow us to look at sensitivity in terms of brain abnormalities across different data types, and also hopefully serve as a valuable resource for thinking about next steps in terms of analytical approach. So we could take different sort of voxel-based approaches. So obviously Matthew mentioned about voxel-based morphometry, making these more automated, thinking about approaching things like brain age, normative modeling, using things like machine learning, different types of models applied to diverse schizophrenia spectrum disorder populations, thinking about how we might use different neuroanatomical profiles, so thinking about stages of illness from clinical high risk through to more established schizophrenia, as well as hopefully identifying new data that would allow us to explore bipolar disorder, major depressive disorder, generalized anxiety disorder, to create a more transdiagnostic resource. And obviously the next phase that we're really trying to get funded, I suppose, is thinking about how we might also add in new data types. So obviously this is focused on T1 weighted structural images, but it'd be really nice to try and think about the relationships that we could explore within the Psy ShareD data resource as linked to things like resting state, fMRI, DTI, as well as magnetic resonance spectroscopy, that we've been exploring as well in smaller samples. So I'll stop there. This has been shared by Paul previously. So thanks everyone, and I'm happy to chat about any questions.
Okay, can you hear me? Thank you, Jack. Any questions for Jack? And remember to speak rather than...
Yeah, I don't have a question. I mean, great work and everything. I just wanted to mention something that may be relevant to many people, and I've put the links in the chat. So we have been running for the last year an online educational program, which is about disseminating tools called translational neuroimaging. You can see both the links to the website and also to the YouTube channel with the actual presentations that are posted immediately after. This is free, and so you might want to have a look at it to see if there's any tools that people have developed that might be relevant to Psy ShareD, of course, as we move forward. And my sort of request for Matthew perhaps is that you might consider doing a presentation on the VBM tool, you know, sort of half of it how to use it and another half of it clinical applications to date. We organize everything, it's completely free, and so far it has been attended over the last year by more than 4,000 people. So it has a very wide reach. So Matthew, so it's a skills development essentially program, but you know, it has also a component of what can you use this thing for, but it's essentially for people to disseminate different pipelines and tools that they develop and how they can be used. So something for you to consider, Matthew. I don't want to take much time because we're at the end of the hour, the allocated time, but I think that would be a nice thing if you were willing. You don't have to do it. You can ask your PhD or your other students to do it. A lot of the presenters are early career researchers showing off the new tools.
Yeah, I'm happy to do that. I'll probably wear a Psy ShareD t-shirt or something and drop a few Psy ShareD adverts in. But yes,
you know, I mean, absolutely, it has such a great reach that you can definitely use it to include awareness for Psy ShareD, of course.
Put a few slides in on Psy ShareD as well, I suppose. And yeah, Sophia, thank you for that link. Ruba, can you see that link that Sophia has put on the chat? I'm just wondering if we could put that on the web, you know, maybe putting something like that, a link to these websites and resources on Psy ShareD News might be useful. I don't know if you can copy that, and then, you know, next time you're in updating.
So when Matthew does his presentation, you can actually put the video with a tool on your website.
Let's do that. That'd be great. Okay, yeah.
So Matthew, now you can escape.
You've been recruited to do another presentation. Yeah, we're just over time. I don't know if anyone's got any very quick questions for Jack or just more in general. No, I don't think so. Jack, just one thing I was going to say very quickly, just in terms of some of the analyses you suggested around sort of genomics. I mean, one weakness of Psy ShareD, I think with the exception of maybe some data that came from Munich, we don't really have sort of genomic data. And I'm wondering if you're aware of these sort of the sort of open access transcriptomics, if I'm saying that right. It's one of those really long words I always pronounce incorrectly. Yeah, these maps that I think allow you to sort of they're kind of like templates that allow that have information on gene expression, I think, and sort of receptor densities and certain proteins and things in the brain. I'm wondering if that could be something that we could probably, in the absence of individual level genomic data, that we could use in the context that you've described.
Absolutely, yes, I think it's important. I think the challenge with things like biobank is it's not very well characterized in terms of the sort of imaging data that we have. So we've been applying sort of that to the biobank data, whereas actually we could do that with the Psy ShareD data and applying, you know, sort of, yeah, like you say, these sort of O-link data and different sort of omics databases that we could link in various ways. So the work that I presented was using Mendelian randomization, which I think would be really nice to try and replicate some of that idea, looking at genetically predicted changes in brain structure within the Psy ShareD database using some of those large genome-wide consortium databases. Absolutely.
Okay, great. Look, we're over time. I just want to say thank you to everyone who's attended today. A particular big thank you to everyone who's spoken, and you know, and all the people over the last 2 years, some of whom are still here. Sort of people are sort of numbers are dropping off, but who've contributed data and really just sort of made this whole thing a success. And yeah, just looking forward to sort of building the resource and working on collaborations and building the resource further going into the future. So yeah, thank you everyone who's here today, and hopefully we'll see and speak to you all soon. Okay.
Thank you everyone.
Goodbye.